Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thanks for coming to the talk. So today it's our great pleasure to have Professor Randall Burns from Johns Hopkins University. Professor Burns is Associate Professor at Johns Hopkins University in the Computer Science Department, and he is a founding member of Johns Hopkins Institute for Data-Intensive Science and Engineering. And then Professor Burns got his BS from Stanford University, and then MS and a PhD from UC Santa Cruz. And then Professor Burns has very good industry experience because he worked as a research staff at IBM Manhattan Research Center. So without further ado, let's hear Professor Burns' talk.
Thank you. All right, so I'm going to talk about high-throughput data-intensive computing and basically give you an overview of some work that we did in the context of scientific computing, that Yahoo did in the context of cloud computing and workflows, and then the merger of the two, which is where we are right now. And so this is sort of the last 5 years after MapReduce really took off. There became a big interest in figuring out how to do resource sharing among multiple MapReduce jobs. That's the topic of the talk. So this is a Prezi. If you haven't seen a Prezi before, it's essentially just as bad as PowerPoint, but has the additional benefit of making you seasick. But it entertains me a little bit. And so it's a zooming whiteboard model. And so if you feel nauseated, feel free to leave the room. Okay, so this work started in 2008, 2009, where we were looking at scientific databases and trying to figure out how to take multiple queries and allow them to share I/O. At the same time, in 2008, Chris Stolson and his PIG group at Yahoo were working on merging MapReduce jobs. Our work has subsequently gone on to look at shared jobs in scientific databases, where jobs here is a simple form of a workflow. It's essentially an iterated workflow rather than a branching workflow that's important for our users. A finer-grained optimization called shared streaming I/O, where we actually take reorder data access patterns into sequential streams for coherency and improve throughput. And then the latest work is the team that worked on the scientific computing stuff. The student went to Yahoo, and we had a big wedding, and have been working in the cloud again, in Nova, which is Yahoo's workflow engine, in Pig, which is a semi-declarative programming language on top of MapReduce, and in Hadoop. So workflows means joins. I think joins is a really important part of making this type of shared scheduling work, and joins are a little more difficult. So I think the big takeaway, so if you wanted to leave the room right this second, the thing that you would need to know is that sharing I/O is not enough. So if you look at multiple workloads and they have common data requirements, just taking the two workloads and making them share the I/O is not minimizing resource consumption and maximizing throughput. There's a lot more opportunity to share network access, to share memory access, all the way through the memory hierarchy even, and co-execute programs. And this can be realized by taking batch-oriented programs and coalescing them into one program. Right? There are tons of security implications and other things that go along with this, but we're looking from a resource usage throughput standpoint. We're going to take workflows at the end of this and put them together and run them as one program, so that as you access data through the whole memory hierarchy, it's being accessed once and delivered to programs. Okay. So the MapReduce perspective on this problem is that MapReduce is a scan engine, at least in the map phase, often in many subsequent phases. Sharing scans allows you to reduce usage among multiple jobs, and the networking and memory cost as well. I already hit that. And so the goal here is going to be to co-schedule multiple MapReduce jobs so that they use the same partitioning functions, that they use the same shuffle functions, and can share reducers. and based on code rewriting. And that's where the cloud work came from. The scientific database work is that we've got these batch queries, and when you get multiple batch queries against a data-intensive service, we see a throughput collapse. Any one user can sort of use all the I/O resources available in the cluster. So the queries have, again, common data requirements and use common indexes, and so we wanted to build a multi-query optimizer for sharded databases. These actually turn out to be the exact same task, just in MapReduce and databases. And so ultimately the same algorithms and the same I/O techniques work. It's a little bit easier to coalesce database queries than it is general MapReduce jobs, but the end goal is the same. Okay. So as a start, I'm going to review this first result in I/O sharing for MapReduce that's from the PIG team at Yahoo. And so they observed that many MapReduce jobs are essentially just very lightweight maps that then compute simple aggregates or do almost nothing in the reducer. And at this point, MapReduce becomes simply a scan engine. And the examples that they have are OLAP, log processing, web crawling. And so most of this work is in these scans, and these scans can be shared relatively easily. So this is the low-hanging fruit. And their approach was to take jobs and put them into job families, in which a job family is a set of different tasks that access the same file or scan the same files, and then to execute these job families in batches according to some different principles. The highest throughput way to do it to minimize maximum latency, is to do FIFO ordering on job families. But they actually end up targeting average latency, and they come up with this policy that is a little wacky. And so this is their quote from their paper, which is, scheduling policies revolve around the notion that all else being equal, it's good to schedule non-shareable scans ahead of ones that can share I/O with future jobs. What this means is that they're executing the jobs with the least data sharing immediately, deferring, not jobs, the files that are part of a MapReduce job. They're executing the files with the least data sharing immediately, deferring the most popular files to the end, and the idea is that other MapReduce jobs will then will merge onto that file, and then you can execute a bigger batch. Okay, so I understand the intuition, and the argument is based on if you have an online arrival rate and you allow work to accumulate, the arithmetic works out. It's sort of weird for me because I only know two things in computer science, and that's hierarchy and the greedy principle. And this one is neither. And so a little against my intuition. But for this online arrival rate model, they get a 50% performance throughput increase. And that's mostly just from sharing. So comparing with FIFO ordering, and there's a bunch of policies. I only want you to take an impression out of this graph. And I'm not going to be talking, I'm going to show you some graphs. For the most part, they're going to have things like oblivious FJF that I don't remember what it is, much less want you to care. But so 50% throughput increase is nice. And this is on their, this is on workload derived from their internal, they call it the grid, the internal grid at Yahoo.
This is assuming that there's a lot of common overlap between subsequent jobs.
There's a lot of data overlap between the jobs. Yeah, so it's they're scanning the same log files, they're indexing the same web pages.
Reasonable short window, right?
Yeah, well, within the duration of the job, right? And so this is all in this batch computing model where jobs run for minutes to potentially hours. Yeah, so that there's also hidden things like how long does the job sit in the queue before it's ready to start executing, how long is the setup time, because if you're going to accumulate work, you need to have, it's much like disk drive scheduling. You need to have lots of pending IOs to do meaningful reordering. You need to have jobs queued up to execute them together.
So I guess the question is, if you have a very large MapReduce cluster, presumably a lot of different data are stored in this cluster, right? So people will go and then do their own thing, and then how common it is to find the data set commonalities in those scenarios?
So the answer is there are systematic reuse of particular data sets. So incrementals on the crawl, log processing, and what Yahoo found is that there's this huge body of data, but there's also new data that was collected or data that's temporal, and popular data that gets reused. And so they're saying that in total that they're getting 50% throughput increase. This is actually going to be the lowest number I'm going to show you. I don't have great insight into their workload, and the later benchmarking results that I participated in that I'm going to show you are from something called PigMix, which is their internal cloud benchmark. So when they deploy services, they've abstracted what the Yahoo workload looks like, published a cloud benchmark for that internally, and that's what we evaluate on. So it's not the best answer to your question. I can answer that question for scientific data, and we'll see it. Okay, so some observations about this first result. So it's job-oriented and has job-oriented completion, which means that your measure is if you submit a job and the job's going to scan 1,000 files, your measure is when that 1,000th file is scanned and completed. And so it doesn't really account for instantaneous throughput. Waiting time doesn't accumulate against any individual file, right? You don't care whether you do a whole bunch of work at the front and one piece at the end. It's not clear that that's appropriate. It ignores caching. And this is going to be important because when we tackled the similar problem in parallel, we came from a very different standpoint. We used greedy principles because that's one of the two things I know how to do, and because it allows for some caching opportunistically, that the data that's in your buffer pool is getting reused, and so you've got your most popular data in the buffer pool, and you're getting opportunistic reuse and avoiding I/O actually. That it ignores bursty workloads, right? If you get a burst and you're deferring all your work for later, I guess the thing is just this idea that your system is always consumed in that doing unpopular IOs is the same as doing popular IOs, where if you had a bursty system, you might want to be greedy and get the maximum throughput of your popular files immediately. And there's no guarantees on starvation. Okay? But good throughput, nice starting place. I'm now going to seg, because this is where I get some skin in the game and we get into some of the work that we did in my lab. And so the rest of this talk is structured as followed. I'm going to give you a sort of brief overview of our ideas, which is an Institute for Data Intensive Engineering Science at Johns Hopkins. Some of the data sets and applications we work with, and that'll provide some motivation for, that's then the specific data-intensive turbulence database cluster service that we provide, and then all of our scheduling work. And this will be a brief overview of batch scheduling for jobs, streaming scheduling, and then on into join scheduling. All right. So the Institute for Data Intensive Engineering Science, we've been at it for 3 years. We've had the Institute. We've been collaborating for 12 years. I've been there 9, and this all started when Jim Gray, who used to work at some company in Redmond, came and started collaborating with Alex Allais on the Sloan Digital Sky Survey. So this is essentially taking an optical telescope, mapping the sky, putting it in a sharded database, providing public access to the community. And was the first demonstration of the impact that data-intensive science and sort of clustered databases can have on science itself. And so notably, the Sloan Digital Sky Survey is the most important telescope in the world. More important than Hubble, more important than Swift. And it's not because it's a great telescope. I mean, don't get me wrong. It's a perfectly fine telescope. In the world of telescopes, I'd be happy to have this one. But what it is everyone can use it. It's never cloudy. It's a community resource. It allows for arbitrary reuse, retrospective studies. And so just the semantics of being able to access this data, to write different queries, to do hypothesis generation and refinement has made it that this is the most used telescope. And we've been hosting that for a dozen years. We've gone on to expand into lots more data-intensive science fields, so high-energy physics, computational fluid dynamics, which is kind of my interest is in, or the data sets I'm most involved with are fluid dynamics, brain connectomics and imaging, and astrophysics. But in total, we're spending about almost 3 petabytes now, which we think is big. Now, the comment, and I made this to Cheng earlier, is that I think of large data computing in academia as being an order of 100 times bigger than what you can do on your desktop and 100 times smaller than what big companies do in the cloud. And that 100 number is pretty disappointing for me, right? But so I'm think of it as a 1% observation of the reality of large data. And our data set sizes tend to be in this 100 terabyte range. With a couple of exceptions, notably scientific data sets, that seems to be a natural size that you can accumulate on funded projects. To get the bigger data sets are coming from something like an accelerator or the LSST, which they don't seem to be able to manufacture, except for lenses. And so that these individual petascale data sets we're just not seeing. That the biggest simulations, if you take a meaningful set of observations from them, produce hundreds of terabytes. This will certainly scale, but right now it's not petabytes a data set. 5 years ago we built the Gray Wolf system. It was named after Jim Gray. It was supposed to be a Beowulf-like clustered system for databases, hence the name. It's essentially commodity storage, top-of-network switches, 2U servers, 4U storage, 48 disks server, running Microsoft SQL Server. And at the time, it's a petabyte system, completed 3.5 years ago. It performs 70 gigabytes a second of I/O through Microsoft SQL Server database. So that's the query output that we benchmarked and won the 2008 storage challenge at supercomputing. I was disappointed that the plaque they gave me was so blurry. I mean, it's unfortunate. So that's sort of still our baseline architecture. We went on to explore new architectures, and this is our atom ion cluster. So this is low-powered motherboards with integrated GPUs that are memory mapped, some SSDs, some hard drives. The whole thing cost $30,000, and this is 2 years ago. 36 nodes, 1.2 kilowatts, $30,000, doing 18 gigabytes a second of raw I/O. And so this is was our exploration of what you can do with commodity hardware. And the ideas behind this were driven by Gene Amdahl, Gordon Bell, and Jim Gray is to tune the processor capabilities down to get a system with I/O balance. There's been another paper in this space that's really quite good. You might have heard of called Fawn by Dave Anderson at CMU. Explores this same design space. And so this is not a cluster that we're going to deploy data sets on, but it was an interesting experiment and fed into the cluster we're currently building, which is the Datascope. So this is an NSF. Yep.
For the Sky Sloan or whatever the name was, what's your typical throughput on that system, to compare to what your system can actually do?
Okay, so the Sloan Digital Sky server has, we probably are running 20 of the Gray Wolf nodes on that data set, so that it's a multi-tenant system, right? And most of them are relatively low throughput, high query, education, samples, casual use. We also have a batch service called cast jobs that is the high throughput users. And I think we're doing 5 gigabytes a second out of it. So not a huge fraction of the aggregate bandwidth of the system. And I'd say that characterizes Gray Wolf. Like Gray Wolf, like most MapReduce clusters, ends up not getting the workload to tax all of the hardware. Good question. Yeah. So the system that we're starting to assemble right now is a $1 million NSF-funded data scope. It's supposed to be a microscope for data, essentially. And it's I don't want to go through all of it. It's a heterogeneous system that combines multi-tiers of performance and storage, has GPUs and SSDs combined. And so some things that we're going to do, it's going to be 5 petabytes and change and do 460 gigabytes a second of I/O. And so this is what data-intensive computing looks like at the edge in academia. And the node count is 100, right? So pretty small. Okay. So one of the multi-tenant data sets is, I'm doing great, okay. Computational turbulence. And this is actually where this talk starts from. I normally give a turbulence talk to more sciencey crowds. So these are giant fluid simulations, 1024 to the fourth, that output hundreds of terabytes to petabytes. Typically in computational fluid turbulence, you're analyzing dynamics on the fly on a supercomputer as you're doing the simulation. They store a few snapshots. This is tradition, but what if new questions arise? Like you need the time evolution of data, or you're in the situation now, if you've already run the simulation and you didn't collect the statistics you need, you can resimulate, or you can keep these massive data sets to reload. Either which one of you need to have a supercomputer. And what we want to do is use data-intensive computing to decouple high-resolution fluid dynamics from supercomputing. And we do this by storing all the data. Let's ignore that quote. And so we take an entire simulation run, hundreds of terabytes. So we're taking 1/10 of the snapshots that are computed in this direct numerical simulation. And that number is, you need to compute at a finer granularity than you need to track particles at or do statistics at, just for correctness criteria. And then we build these 100 terabyte data sets, and they're available for ad hoc inspection, for data mining, for feature extraction, find me interesting turbulent structures, what's the pre-evolution of this vortex, public access, and it's also retrospective studies. So we're creating a service that's beginning to get used in the turbulence community, like the Sloan Digital Sky Survey gets used in the astrophysics community. And this database, in some sense, stores the computational effort. You do this giant simulation, you store the data, that captures that simulation so that it doesn't need to be repeated and you can access the output. It separates the simulation, the solving of the equations, from the experiments. So you actually conduct the experiments on the data output, separated in time, separated in space, in a different computer system, in this data-intensive environment. And it's been a really powerful tool. It's also allowed people to do new classes of experiment that aren't possible in simulation space. So you can iterate back and forth in time. You can't run simulations backwards. And so they destabilize. And so there's studies about like the pre-evolution, like if you see a feature, how did that feature form, that people are executing on this database that are not possible in a supercomputer. So that's the value proposition of this cluster. It's a web services cluster. This is our front page from a couple months ago, and this is the number that we like, which is 52 billion points queried, right? So it gets used, some. Not ridiculous amounts, and it's a sharded database. It's kind of what you'd expect. We take the turbulence space, we decompose it spatially, by time step. We shard the spatial decomposition onto multiple nodes, and we use a mediator. Again, it's all SQL Server 2008 in this case. And you access it from web services. So R, Fortran, C, Python, our major user community is Fortran. I appreciate the irony of using Fortran and web services. But it's that easy. It's a Fortran call out. I have a code example. I think I cut it out because you don't need to read Fortran. I guess the workloads that this service presents, and this is going to be the last slide before we dive back into scheduling, which is what I care about, is how when you design a service like this and people want to conduct queries against these simulations, you present them an interface. And there's interfaces. The interface design process was interesting. And where we ended up was trying to create an interface that allowed for batch scheduling. Because if you give too low level an interface, if you, for example, allow people to say, get me the velocity or gradient or the point, or get me this energy at this one location, and they're submitting these one at a time, there's both a huge cost for web service invocation, and there's little opportunity to do optimization and reorganization at the service. This is sort of the database argument, right? If you give me your query and you tell me what you want, I can reorganize it to optimize it. Now, to a higher level, if you say, tell me the evolution of 1,000,000 particles through 1,000 time steps, that doesn't provide enough insight into the experiment. So we decided on an interface which is essentially to give batches of points. So batches of points tend to be 10,000 to 100,000 in size on a time step, and then allow the database engine to compute gradients, filters, kernel computations, and this is the active database principle. So we're trying to capture the compute at the data on the databases using user-defined functions, and then the client code can do some minor customization. So if you want to track particles, you will ask for smooth, interpolated velocities at all these different points, get the velocities back, update your particle locations, and ask for new velocities at the next time step. All right, back to computer science. So you're a computer science at the university. You spend your $70 trying to build a data-intensive computing system. You do it, and the only thing that can happen is you can fail or you can succeed. And this was Jim Gray's comment about the Sloan Digital Sky Survey, and I loved it. And so we build this, and people use it 52 billion times, but all of a sudden we're I/O bound. 80% of our time is loading the data. We have DB queries that you can write one line of Fortran that'll launch terabytes of data access. Scans last hours to days. A single query can consume all the I/O resources, and the more popular your data-intensive service is, the more it collapses. We don't have the ability from an investment or resource standpoint to do dynamic replication and create new instances, and even if we do, we're I/O bound, so we need to copy all the I/O as well, copy all the data to get new I/O resources involved. This might be amenable to some content style caching, like taking the popular data out, and we do that some, right? Like we take popular data out and instantiate a separate service. But at the end of the day, people are scanning large data sets, we don't know what they're scanning, and we get big I/Os. And so this graph just shows that we have queries depending on what computation you ask for at the database that last for 10 to the third seconds, pretty commonly for a reasonable number of points, for 10,000 points. So, okay. So we went to tackle this problem using this notion of shared scans, and that's where we started. We started with these I/O services that were choked, and we wanted to provide data-driven batch scheduling that essentially co-schedules queries by the spatial subregion that they access. So looking at queries that access the same region of time-space, or in astronomy, same region of space, co-schedule them. We also wanted to tackle starvation and coordinate the caching with the scheduler. And so this is where our approach ends up being different from what happened in MapReduce. In MapReduce, you sort of instantiate a MapReduce computation, you define all the mappers, you do the computation, you tear it all down. Right? That's not the way databases work. Databases, you do queries against the database, you have an instantiate of the database, the buffer pool carries from query to query, and so there's a lot of benefits of caching. So for astronomy and astrophysics, what this looks like is you have a space filling curve index, so the circle's a spatial index, just like a partition cube. They use the exact same data structure, use a quad tree. And so you'll have SQL queries, which are select from where, and we'll use some user-defined functions like a nearest neighbor function or a filter function. And these queries will define subquery regions. You can partition a query based on the subspaces it accesses. You can then reorganize these subspaces and essentially take the three queries, query 1, 2, and 3, to the blue subspace and execute them in one I/O. So this is where we started, just on I/O as well. Do the reorder and the co-scheduling. The co-scheduling has some secret sauce that does some time age weighting to prevent starvation, and we do things by most popular queries first. So we actually get worse batching in the sense, but we are greedy, and we are greedy because of the cache. And so with the cache, it actually turns out to be beneficial to be greedy. We ran this experiment because we published our paper, they published their paper. People said, you got it backwards. And we ran it, and we only got it backwards if you don't cache. Caching turns it upside down, which I thought was interesting. Some observations is, so these are the top 10 spatial regions based on the database. There's a fundamental partition size that underlies the database. And so I think each one of these is 8 meg. And so the top regions get lots and lots of repeated reuse, and all this is in the cache. And it goes to, there are interesting things in the sky. There's a whole bunch of data that's interesting, a whole bunch of data that's not interesting. I don't think that's very profound to say that there are interesting things in the sky. And so here's the big picture is if you don't do any sharing, you get, can't be 0.1 queries per second. But when you varying the starvation resistance bias, you can double your throughput. And so I think that doubling our throughput is better than 50% improved throughput, but that also reflects that we have a lot more locality and cache locality to exploit than they did in MapReduce. Okay. Now, as we went to turbulence, we started to look at going from these query sharing to job sharing as a way to get towards workflows, right? Because queries are not, people don't do individual queries, they don't do individual MapReduce jobs. They do MapReduce jobs in workflows, they do queries in sequences of queries and jobs. In turbulence, this has a very simple form, which is you're doing iterative queries to time steps. Sometimes strided, sometimes backwards, sometimes forward, but there are these access patterns. And so the idea is if we had queries that accessed regions R1, R3, and R4 here in LifeRaft, that there's this opportunity for sharing among R3 and R4 that LifeRaft won't access because it doesn't see it's trying to schedule query R1 and query R2. And so if you then add some job awareness to look at, actually do some loop unrolling and ask, what are all the things that are going to be accessed, you can merge the streams and improve the performance. Pretty simple idea. It has solving this problem has a database query optimizer feel. You do in dynamic programming, algorithms of high polynomial complexity. I think there's an n-squared phase and an n-cubed phase, but that's how databases work, and it works okay because there's not so many queries. So we greedily assemble the amount of pairwise job sharing as a dynamic program, and then we look at assemblies of these pairwise. This is a very confusing picture, but I guess the one thing is that each one of these horizontal lines is a sequence that corresponds to a job. These blue lines represent dependencies, which are called gating edges in a representation. And so that after this finishes R2, it's going to do this single region 3 job on one partition of the database, that is a low throughput job, but it enables all 3 queries to go to R4 at the same time, right? Just like the intuition. And so the process of doing the optimization to schedule this is to take the jobs, to build these gating edges, and then to assemble the gating edges in a global schedule. It's not very efficient, small instances. The query optimization efficiency is not a big deal. These type of relatively slow, high polynomial complexity query optimizers are used in joint processing all the time. And this is now better. This is a 3 times improvement. So no sharing versus job awareness. We compared a couple variants of LifeRaft in between and decomposed it to see where the benefits come from. So 22% of the benefit is from query reordering. So just as regular LifeRaft being able to do things based on the amount of sharing. 12% from something I didn't talk about, but 30% more comes from this joint awareness. Right, job awareness. So this understanding these job sequences and being able to look at the iterative loops and schedule based on those is very valuable in achieving this throughput improvement. Okay. Yeah?
Maybe I missed this. So I understand your point about trying to schedule jobs that are the same across different tasks together. That makes sense. How does a program specify what each one of these jobs is in that sequence, like R5, R4?
So there are declarative interfaces which you can use as hints, and we will do it like prefetching too, where we will look at strided access patterns and try and figure out what a loop is going to do. So if you have a program, right? So you write a Python program that says I want to iterate over these time steps. Here's 1,000 points. Call a batch of get velocity, or batch of get velocity gradient. So we're going to see the first one, we're going to see the second one, and we're going to assume strided access, and it just works because the patterns are so simple. So you can either, if you want to program to it, declare it.
You have to inspect the code then?
The mediator in this mediator architecture is doing query rewriting already, right? Because it's getting a query that's to the global database, rewriting it for the sharded database. That mediator can also look at what time step it was on, what time step the previous one was on, and it's a simple process that works.
Okay.
Yeah.
So, do you have the response time figure?
For this, the response time figure for joints. The response time is sort of a weird one because response time ends up always going down because you're increasing throughput. And I think that's the way it gets reported, and it's sort of not good enough, right? Because there's also response time variance, which is in a way more important. Like anytime you take a service and you increase its throughput, your average response time is going to go down. No? This is Little's law. Yeah. Your average response time is going to go down. Right? So we're concerned not only with average response time, but the response time variance, so how predictable is the service, and the response time maximum. In this data-intensive world, people tend to punt, which is to say, data-intensive batch-oriented computing, these jobs already run for a long time, we're not going to worry about it, we need starvation to be bounded and reasonable. So this was this figure. So this figure is looks at this 1 to 0 is essentially how starvation resistant we are. And I didn't talk about this. But so this is the throughput if you're very sensitive to starvation. So this is actually reduced response time compared to no share FIFO ordering. And then this figure is if you're not starvation resistant. And the response time here is more than, the maximum response time is here more than double. to give you an intuition. And so there is this knob that says, if you're starvation sensitive, you can still get some benefits, right? Because you're still sharing, even if you're scheduling things to try and enforce good completion orders. But if you're completely relaxed about starvation, you get more and more throughput. I don't have a great answer as to where you want to be, how you want to tune this parameter. And the other thing about this parameter is very workload sensitive. So when you present a little bit of load to the server, you want this parameter tuned all the way to maximize sharing. And when you get a lot of workload to the server, other way around. But the point is there's no, this parameter needs to be tuned dynamically. So it's very difficult. All right. How am I doing? Okay. So this is appearing this year in 2000 in supercomputing and is related to the notion of batch scheduling. It's not really on topic, but it's inspired by the same set of ideas, and the results are great. So I wanted to throw it in there. A lot of these computations in spatial databases are doing kernel computations, smoothing, gradients. Lagrange interpolation is the most important one. And so this means that you pick a random point, a target point, in this case x prime, y prime. There's a set of grid points around it that define the kernel that's going to participate in answering that query. And again, our queries consist of batches of points, so maybe 10,000 points per time step that are being delivered, right? And so what this means is that we end up with a series of kernels in green here on different fragments of our data, the blue, and then subqueries associated with each one. So these represent that that P1 has a subquery on region 0. Now they're shared regions, and the idea is again a pretty straightforward one, which is to take the data, to iterate over it in a linear space-filling curve order. So even though you're not inherently a streaming workload, to treat it like a data stream, and to execute from 0, 1, 2, 3, 4, 5. You can see this is what's called a Z order. 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? It's as opposed to row major or column major. And by the way that you can accomplish this is if you have decomposable functions. So if your kernel function can be decomposed into partial sums and computed in parts, you can essentially exchange memory, which is having all these partial sums that you're accumulating, for I/O coherency and sequentiality. And so that's the idea. We do all our I/O now in this database service in a streaming pass, and this was a really wow result for me, because I thought this was going to be a nice little thing, but it's a factor of 10 more efficient than the naive implementation, which is to do each query. And so there's two things that are happening. One is that you access each data element once. So you never access something in a kernel and then come back and access it later when your space-filling curve circles around. But more importantly, all of your I/O are aligned, they're sequential, they're concurrent, so they fully exercise all the parallelism of the hardware at every level.
Is this a special property of the Lagrange interpolation, though?
No.
These blocks together and reuse the computations?
No, so that most of the functions that you want to do, differentiation, integration, can be represented by partial sums, right? So like the computational integration method is and so it applies to everything we want to do.
If I were computing, say, different linear combinations of regions, right? The regions might overlap, but I might not have, or unless I could find some, I don't know, Krylov subspaces, or I don't know what, some things that I could reuse amongst those, I might.
Right. What the property you actually need is you need to be able to look at, so you have a kernel. You need to be able to look at the data element of the kernel, independent of all the other data elements in that kernel. It's not that the jobs interact. It's that that as long as you can, you don't need to have a global view of what you're computing. So there are plenty of examples of things that don't work in this model. For filtering, integration, differentiation, interpolation.
In general, it's that, I mean, you can reduce big data down to smaller data, right? You can use less of the cache because you're looking at this whole region and saying, I'm going to compute something and summarize that rather than have to keep reloading the data.
So here's what happens is is for this kernel, right? You're going to start the solution at 0. You're going to create some memory to allocate it and add the partials from 0, add the partial sum from 1, 2, 3, 4, 5, 6, 7, and then you have to wait and keep that in memory. So for every partial sum, you're spending memory. And we actually measured the memory bandwidth as part of this to ask a question like, you're not completing things, you're accumulating them, and is that important? And the answer is no. That for it's hundreds of megabytes of partial results. So in the worst case. And so this notion is pretty powerful, and it reflects what people have learned in GPU programming, for example, right? Which is you need to do coherent access to data throughout the entire cache hierarchy. One way to go ahead.
Question about the system. So you have an intermediate layer which interprets all the workload and try to write them, and then give to individual nodes to execute it.
This optimization is done on the individual node.
Okay, so individual node is on SQL Server.
Yeah. So
how do you interact with the SQL Server?
Well,
try to reorder things before you submit things to the SQL Server.
Okay. So the mediator. So we have a series of SQL servers. We have the mediator is not a SQL server. It's taking queries, doing query rewriting based on the spatial and sending these subqueries to the individual SQL servers. So when we want to do something like merge queries, we're taking 2 queries that are queued at the mediator, rewriting them as a merge query against the shard, the database shard. So then this optimization has to be done at the database because it's actually about the way you iterate over the data. So we've rewritten the query execution engine both in this mediator level, which is abstract. It's rewriting SQL, but at a pretty simple level. Like if you have a user-defined function or predicate, we don't even look inside it, right? We're taking tables and dividing them by space, and then this query execution strategy is inside a user-defined function. So the user-defined function is interpolate around this spot. And the implementation of the user-defined function used to be grab the data in the kernel, perform the interpolation, return the point. And now the implementation of that user-defined function is generate the partial sum and populate it as you do a data stream. So, yeah.
Are there any data dependencies between different queries?
So everything I'm showing you right now is read-only queries of. Yeah. That issue is going to come up a lot as we move on to graph-oriented data, but we try very, very hard to make things read-only, and if we do read-write, to have a read-only big database and then write to a separate area. Yeah. Not the most satisfying answer, but that's what we do. So one of the ways to visualize how you get this 10 times improvement is by looking at the effectiveness of read ahead and the number of physical reads. So with this streaming I/O kernel computations, the number of physical reads is this blue line, and compared to the red line. So this is 1,000 fewer physical reads. And what's happening is that because we've created this sequential pass over the data, this is the effectiveness of of read ahead. Right? So we're essentially getting all the I/O done in read ahead by the subsystem. We've created an I/O stream that the system understands and works well with prefetching hardware and prefetching policies in the operating system. All the data gets delivered, and by the time we consume it, it's there. Right? And so when you compare it, if you do this direct evaluations, what D stands for, read ahead is essentially totally ineffective. Right? So the outcome is just take these queries, rewrite them globally so they conform to the policies the operating system expects and the database expects, and it flies. So that was fun. And this is sort of the end of the data intensive computing portion of it, which is that this I/O sharing and data streaming is really important for high throughput science. Right? It's the difference between having these services that don't work at all used by 10 users and these services that don't work at all used by 100 users. I mean, it's just a different pain point. Right? And our experience is that pretty much as many people will use it as can slow it down. But what we need, we're all about supporting concurrent users and public accessibility. And those are the people that the service is most valuable to are people that want to do computational fluids that don't work at Los Alamos. Right? So we have a guy at the West Point that this service has transformed his life. He went there, used to be in graduate school, had supercomputer, has no supercomputer time, and has been able to just convert his research to this and do it for free. People that work with big data systems in the cloud and industry already know this, but it's a lot more difficult to scale I/O than it is to scale out either computer capacity. It's just not the shareable resource, and it gets very congested. These type of data sharing techniques are valuable. Okay. So, last thing. This is our latest result. So we sent Dan Wang, my student who's going to Salesforce, graduating this year, to Yahoo last summer to try and get this all together. And so we went back to the cloud, and we're going to try and take some of these database techniques, starvation resistance, caching, and apply them to Pig, Hadoop. Nova is their workflow engine in Yahoo, and tackle the big problem, which is to eliminate redundant processing, to go from just scans and actually do the entire programs so that we can get these memory benefits as well. We want to share reducers, so we transfer the data over the network once, and we want to adhere to soft deadlines. And so be able to control this latency throughput gain goes to the question that was asked earlier. Okay. So what this looks like is you get workflows. We run it through a workflow merger. In this case, that we have a job here, C2S0, that can be merged, and we merge the workflows. Now, this merge workflow, it's only one element. That actually is an entire MapReduce program, right? Or a Pig program. And so that means that merge workflows shares the splitter, shares a combiner, shares a shuffle. And we take MapReduce programs and we rewrite them to align the partitioning functions and run them as one program. And you also share the workflow costs, which are substantial. The startup and teardown cost for the MapReduce environment. It's funny because workflows are a great concept, and we've got this figure where we show we merge one part of our 10-step workflow. The benefits are actually come from, we started earlier saying that many MapReduce programs are sort of simple maps that with nothing reducers, and that applies here as well. That the data on these front-end stages are so much bigger than the data as it goes through aggregates. Yeah.
Are these workflow programs mostly in Pig?
They're Nova.
Nova. So I don't know what Nova is, but it's similar to Pig.
It's a workflow engine on top of Pig on top of MapReduce. Right. So
I guess my more basic question is then, is it easier to do this merging because you have a structured type language like SQL run, or something like Pig running there that allows you to merge this together, versus say a user-defined function that you write in and plug into MapReduce, which makes it quite a lot harder to merge.
So, okay, so each dot here is a pig or MapReduce function. Nova is the system that allows you to connect up these MapReduce functions and run them, right? The pig is not SQL enough to do the type of optimization you're talking about. So what we end up doing is taking map programs that apply to the same data, realigning their partitioners and their restrictions on how you can change the way that map input works, and then essentially running two programs aside, rewriting a map that is map 1, map 2. Right? So we're not doing any fine-grained program rewriting.
It's more the principle of just aligning the map jobs together.
Yeah, and there's safety restrictions. You could get a lot more if you could look inside and do query optimization. Like you might be doing two joins that could be shared. We can only see the joins we can see some joins, but you can do stuff inside the program that we won't touch. Right, and so this ends up, and this actually goes to the question you just asked, which is that all the I/O gets shared when you have shared joins. So this is 3 jobs against these ABC inputs, and the takeaway here is if you execute them separately, they have an I/O cost and a computation cost, and that if you execute them together, you can share the I/O cost, but the computation cost will be somehow reduced, right? Not all the computation, it's not redundant. And so we see some benefit there as well. And the takeaway is for the PigMix workload, which is Yahoo's internal cloud, they call it grid, benchmark. This ends up being sort of better in every dimension. So this is no sharing, and these are all the different variants that got tested with. But the takeaway is you're using fewer resources and meeting more deadlines for all the variants. Fewer resources because of sharing, and more deadlines, not because it's more fair, but because the higher throughput reduces average latency and gives you enough wiggle room to meet more deadlines. It's less fair, right? And this notion is important to batch computing, that fairness in the number of deadlines you meet and fairness in response time are only loosely coupled because there's such throughput differences that come from sharing.
So this is using Yahoo's internal benchmark to evaluate those. And then, how many jobs in that benchmark?
So this was on a 16-node cluster.
16 nodes?
Yeah, 32 cores.
Okay.
It's pretty small.
How many jobs? They look at how fast all the jobs can be?
They have 17 different types of jobs, and there is an intensity knob that allows you to specify the inbound workload, right? So if you want to dig into this, I'm going to actually fail. So there's a door right there. And similarly, more throughput, lower response time. And sort of, this is where we are. In computer science, everything old is new. Many of these techniques have pleasant similarities to tape scheduling. Like there's a whole bunch of work on, I'm going to do a tape scan. How do I merge multiple programs to do these tape scans together? That is similar. This space is more complex because there's caching in the memory hierarchy and you get more flexibility in your rewrite, but this is not a new idea space. Shared scans are better in every way. Like there's no downside to them. And that this streaming technique has huge benefits, and I think we're just starting to look at how generally applicable this is. And so a question for me moving forward is should I take, so it seems like streaming computing has been done because there are inherently data streams in limited memory resources. And what this says to me is that there's value in doing streaming computing on any computation as long as you can represent it as a stream. This is consistent with, so Stanford has had this stream supercomputer project for a handful of years that explores the same idea. Some parallel computing in systolic arrays builds off similar principles. But the notion of doing reordering of jobs to get friendly data access patterns is powerful and needs to be explored much more, in my opinion. All right.
Thank you, Professor.